marked, but the TAs still have to return the tests to me. So as soon as I get them back, I will give them back to you. I imagine the marks will go up sometime, assuming they're all marked. I haven't checked if they're all marked yet. The marks should go up sometime tomorrow or Wednesday on OnQ. I don't know when I'll be able to give them back to you because it depends on when the TAs show up with the physical copies. Hopefully I can give them back to you though on Wednesday or Friday this week. All right, so we've completed, what did we complete last class? Last class we did compare to. And so we're now on to the next lecture, which is enumerated types. All right, so enumerated types are a special kind of class that you can create in Java, well, other languages as well. When you are trying to represent objects, but there's only a fixed number of constant objects. So for example, if you wanted a class to represent the days of the week, there's only 7 days of the week and they never change. Right? Similarly with the months of the year, there's only 12 months of the year and they never change. Right? Suits in the standard deck of playing cards, right? So there's only 4 suits, only 13 ranks, unless you count the Joker. And then there are some other examples which are more questionable. So you might think that there's only a limited number of Canadian coins, which is true, but they aren't necessarily constant. So we've removed the penny recently, and it's possible that we'll add a $5 coin or a $10 coin in the future. So perhaps not a good example. Canadian provinces and territories, well, we just added Nunavut not too long ago, so these are also not perhaps a great example. Planets of the solar system, Pluto is sometimes a planet, sometimes it isn't, right? It's possible we'll discover another planet, so possibly not the best example. Arithmetic operations, though, pretty good example. So if you just consider the basic arithmetic operations, there's only a handful of them. And so if you have a situation where you want to represent objects of these types, then you can use what's called an enumerated type. So these are also called enums in Java, or enum type. So it's a type that represents a fixed set of constants. All right, so you can do this in any language, or you can simulate this in any language. So in older style Java code and in C code, if you want to do this sort of thing, it used to be common, well in Java anyway, that you would use some integer constants to represent your types. Right? So you would create a constant, public, static, final, int, called Sunday, right? And give it a value. So in this case, we're going to give it value 0, right? Monday is 1, and so on and so on and so forth, right? If you just look at the slide, you can quickly see the problem with this approach, right? If you wanted another enumerated type, like the months of the year, right? You'd make a constant, so in this case January, whoa, sorry, right? But you'd also assign it a value, and it's common to assign it, the first constant to be assigned the value 0, which unfortunately is the same as Sunday. Right? So a big problem with using ints to represent these enumerated types is that there's no what's called type safety. Right? So basically we're using an int here to simulate a type. Right? But all of these different types, so the months, the days of the week, the months, and so on, they're all just ints. Right? So any method that takes an int will also accept a day or a month or whatever other enumerated type you're creating. Right? There's no way to write a method that only takes in an int, that only takes in a day or only takes in a month. Right? It has to take in an int. So that's no good. You can do stuff like perform arithmetic with days and months, which might be useful in some cases, right? But it's nonsensical in other cases, right? So for example, I can add Sunday to March, right? Or I can take the square root of December, right? None of which makes any sense. The last one is also useful, right? So one of the advantages is that you can compare days and months for equality, inequality, less than or greater than, right? Because you're just comparing ints. So Monday is greater than Sunday, so you can interpret that as Monday comes after Sunday. Right? March is greater than January. March comes after January in the year. So that's actually an advantage. There's another problem with using ints to represent constant values, and that's there's no easy way to translate that int back into a string, right? Because there's no toString method for ints. So if I wanted to print out the constant Sunday, right? I'd have to write a method. The method would have to check what is the day valid, right? And then it would have to map the day to the appropriate string. Right? And so there's no easy way to print out one of these enumerated constants. I can print out the number, but that normally doesn't tell you very much. So instead of using ints, you can use some other type. Right? So it's also not uncommon in Java to use strings. Right? So instead of using the int, instead of making an int called Sunday, we'll make a string called Sunday. Right? And we'll set its value to be equal, in this case, all uppercase Sunday. Right? And you can do the same thing for all of your other constants. Right? But this doesn't really solve any problems except for the problem of translating the constant to a string. Right? So all of our constants are now strings, so there's still no type safety. Any method that takes in a string will take in a month or a year. Right? It actually gets worse in this case because programmers are lazy. Instead of writing month.Sunday everywhere, right, people get tired of writing month dot and they just write Sunday, right? Which works fine until you decide that you want to change the string that corresponds to month.Sunday, and then you have a problem, right? You can still compare these things for equality, but comparing strings for equality is much slower than comparing ints or addresses for equality, right? Also, if you want to compare these for order, right, you're stuck with the string compare to method. So now Monday comes before Sunday if you just use the plain old compare to. Right? And so so comparing them now breaks in, well, it doesn't break. It just, you end up with sorting in lexicographical order instead of in the order that your constants are defined in. All right, so to get around these problems, Java added enumerated types in the 5th version of the language. So you can see it took quite a while before this type showed up. These are actually classes. So anytime you make an enumerated type, you're actually making a class, right? And the classes, your enumerated classes, they all inherit from this class called enum, big enum, which inherits from the class big O object. So enumerated types, they're just objects. Well, sorry, they're just classes. So you can have fields, and you can have methods. You can even have constructors. Right? Your enumerated types can even implement an interface if you want to. If you have a constructor, the constructors are all private, so you can't access them from outside of the enumerated type. Right? And it's easy to make an enumerated type. That's the enumerated type for day. Right? So you change the keyword class to enum. Right? You give your enumerated type a name, and then you just list your types separated by commas. Right? Now these are all constants, so we name them in all uppercase, right, to indicate that they're actually a constant. How do you use one of the types? You just write day.Sunday or day.Saturday or day.Wednesday, and that's it. There's your constant. Right? So very easy to make in the simple case. So here's a little example of using that enumeration. Right? I can make a day object. Right? I can assign it one of the constants, so day.Thursday in this case, and I can even print it out. Right? When you print it out, you just get the string that corresponds to the constant name. Right? So the enumerated types, you get a compiler-generated toString method, right, for free. You don't have to do anything. If you want to change the string that gets printed, you can change it. You just override toString. Right? So you go into your enumerated type, you override toString, and you generate the appropriate string for each constant. So the nice thing about the enumerated types is that you get exactly one object for each constant that you define in your enumerated type. So in other words, the language guarantees that there is exactly one object that is equal to day.Sunday. There's exactly one object that's equal to day.Monday, and so on and so forth. Right? Because there's exactly one object, you can use equals equals to compare enumerated types. Right? So I can write day.Sunday equals equals day.Friday. Right? And that will return false. Right? So you don't have to use dot equals. You can if you want to, but you don't have to use dot equals to compare your enumerated types. Right? You can safely use equals equals or not equals. And if you really want to, you can always use equals. This is guaranteed to work because the only one that can create the constant objects is whoever created the enumerated type in the first place. Right? So there's no way to make new enumerated objects because there's no constructors that are accessible from outside of the class. Right? So enumerated types, they are in fact types. Right? And what does that mean? You get all the benefits of compile time type safety. Right? So if I have the enumerated type month, right, that corresponds, that contains the months of the year. Oops, sorry, there's supposed to be an example here. Right? Then you can write a method that takes in only a month. Right? And it will only take in one of these 12 months. If you try to pass it a day object, it won't work. Right? Because a day object is not equal to a month object. You can compare your enumerated types. Right? So all enums automatically implement comparable. Right? So the natural ordering of your types is the order in which the constants are defined. Right? So for the month, right, January is the smallest month, right, and December is the largest month. There's no way to change this behavior. So you can't override compare to in an enum. If you try to do so, the compiler will complain. Right, so for example, if I have if we have the days Monday, Thursday, and Saturday, and we compare day 1 to day 2, so we're comparing Monday to Thursday, right? Monday is less than Thursday. And in fact, it's 3 days less than Thursday, right? Or 3 days in front of Thursday. So the value that you get back from compare to tells you the difference in the order of your two types. Of your two objects, sorry. Right? So D3 compared to Monday, so Saturday compared to Monday. Well, Saturday is 5 days after Monday. So Saturday compared to Monday returns the number 5. Right? If you compare two equal days, so Thursday to Thursday, right, you get back 0. All right, so enumerations are really classes, which means you are allowed to have fields. Right? So your enumerated types can carry information with them, which makes them much more powerful than using just a plain old int or just a plain old string. Right? If you have fields, then you have to initialize them somewhere. And so the natural place to initialize them would be in a constructor. When you implement a constructor for an enumerated type, you have to remember they are always private. Right? If you try to make them anything other than private, the compiler will complain. Right? If you don't give them any access modifier, the compiler automatically makes them private. Right? You should also remember that enumerations are supposed to be constants. So if you have fields that are associated with your objects, then the values of those fields normally shouldn't change. Although you can probably come up with a situation where you did have an enumerated type and you had some field whose value does change. All right, so here's the month type again. And this time I'm going to store the number of days in each month. And I'm going to provide a method that returns the number of days in each month. Right? And there's going to be a problem with February, obviously. So the way you create your enumeration, it's the same way as before, but now each object calls a constructor. Right? So the way you write this in Java is you write your constant, then the round brackets to indicate that you're calling a constructor, and then the value, which in this case is the number of days. Right? I need to store this value somewhere, so my type now has a field called days. Right? So every one of these constants has its own field that represents the number of days in the month. Right? Now, the enumerated types, they're supposed to be constants, so I'm making this field final. Right? All right, so we need to add a constructor now. So the constructor is just like any other constructor. Right? It has the same name as the class, so it's called month. For this particular enumerated type, right, that constructor takes in the number of days. Right? And all it does is set this day is today's. Right? I don't have to bother validating this value that comes in. Right? Normally, if this was a public class, right, you would have to validate that number, right? Make sure the number of days is actually valid for any particular month. I don't have to in this case because the only one that can use this constructor is the class itself, right? And I'm implementing the class, right? So as long as I'm sure that I'm calling the constructors with the appropriate values, right, there's no need to do any validation here, right? I can assume that the number of days that's being passed in is correct, or legal anyway. Right? The constructor is private, so you can put private here if you want to, but you don't have to. the compiler will automatically make it private. Now I need some way to give back the caller the number of days. So there's a method, which is public, so you can have public methods. Right? It's called days. It returns the number of days for a given year. Right? We're passing in the year because February is a special case. Right? The way that someone will call this method is they'll have a month object, so something like month.January, right? And they'll write month.days and then pass in the year. Right? So you're still using an object to call the method. So I can check, is the object that's being used to call the method, is it not the month February? Right? So if it's not the month February, then I just return the number of days. Right? Otherwise, I check, is it a leap year? Right? And so there's the code for checking if it's a leap year. Right? If it's a leap year, I just return 29, or the number of days plus 1. Right? Otherwise, we just return the number of days down here. Right? Again, notice here, I can use not equals instead of not this dot equals February. Right? Again, because the language guarantees there's exactly one object that is equal to February. Right? So you basically, so your enumerations are just classes. Right? They have some restrictions on them, but they're just classes. You get some other methods to help you when working with enumerations. So the compiler generates, I don't remember how many, it generates several methods for you for free. So you get a method called values. Values returns an array of all your constants. Right? So for the month class, if you call the values method, you get back an array containing those 12 months in that order. Right? So values returns an array of the constants in the order that they were declared. Right? And so you can print all of your enumerated types like that. Right? You take your, it's static, so you use the name of the class, dot values. That returns an array. You can print the array using arrays to string and print line. Right? And then you get the following output in this case. Right? If you want to iterate over all the months, you can do that. Right? You just call month.values. That gives you an array. You can loop over the array using a for each loop. Right? And you can call inside the loop, I can do something with each month. Right? So for example, find out the number of days in each month for the year 2018. Right? And you would get that. Right? Which just prints the number of days for each month in the year 2018. You also get the method called value of, right? Which takes in a string. So value of translates a string and gives you back the constant corresponding to the string. Right? So for example, if you write month.value of and then May, you get back the month May. Right? So you can check, is M equal to the month May? You'll get back true. Right? That string there has to be equal to the name of the constant. Right? So if you pass in something else, I believe, you get an exception. Although you can just check, just look up the enum documentation and you'll find out what happens. All right, so this one's a little bit interesting. So this is very different than any class you've seen so far. Every object in your enumeration can define its own version of a method. Right? So that's a bit odd. So in the month example, right, the month January can have a method called M, and the month February can have its own method called M, and they can be different. Right? In other words, they have their own implementation. Okay, so what we're going to do here is we're going to make an enumeration that represents the operations that you could do on a simple calculator, right? So I can add, subtract, multiply, and divide. So I want to make an enumeration for the operations on the calculator. Right? Now, when you add two values, right, or subtract two values, multiply or divide, right, there's a different operation that's applied. Right? And so I can use the fact that I can define my own version of a method for each constant to define all of these operations. Right? Now, the way you do this is you declare what's called an abstract method in the enumeration. Right? So let me just show you what that looks like. Right? So here's my enumeration called operation. I've got plus, minus, multiply, divide. Right? Down here, I've got my abstract method. So it's public, then there's the word abstract. Right? The method apply takes in two values, x and y, computes the operation for x and y, and returns the value. Right? Now, when you have an abstract method, An abstract method is a method that has no implementation, right? So notice here, there's just a semicolon at the end, right? There's no body for the method. If you have an abstract method, then in the case for an enumeration, every object must implement its own version of apply, right? So there's no method here. Instead, the methods are defined inside each one of the constants. So inside the plus constant, we implement the apply method, right? And it's easy to implement apply for plus. You just return x plus y, right? For minus, it's just x minus y, and multiply and divide, right? And now you've got an enumeration that represents the operations on a calculator, right? So if you have the operation minus, right, you can take your minus object, pass it in two values, and it'll return the difference of those two values, right? And now it becomes very easy to implement your calculator, right? Of course, you can add more constants here if you want a more sophisticated calculator. Okay, so when should you use enumerations, right? So basically when you have a small number of constants, right, and you're really sure that the values are constant, right? So don't use an enumeration if the objects that you are creating can change, right? Or if you want to add or take away objects from the constant, from the enumeration, right? Once you make an enumeration, there's no good way to add or remove constants, right? As soon as people start to use your enumeration, you're kind of stuck with the constants that you've declared, right? If you try to take away constants or you try to add new constants to your enumeration, then everybody's existing code breaks, right? Because their enumerations are either using constants that are no longer defined, or they're using or they don't have the appropriate constants defined, right? So they have to recompile all their code. So when should you use these? Well, when you really have a small number of values that you want, right? So one of the useful cases for this is when you have some method or constructor that takes in a Boolean value, or maybe an int value whose value that has a small range, right? Say between 0 and 5 or something like that. Right, so imagine I have a class called binary digit, which is similar to the binary digit class that you have in the current assignment, right? If you have a constructor that takes in a Boolean value, right? So binary digit true gives you back the digit 1, right? Binary digit 0 would give you back the digit 0, right? Or you might have a thermometer whose parameter is a Boolean value that represents the scale of the thermometer, right? So true for Celsius, false for Fahrenheit, perhaps, right? Then when you actually use this class, it becomes very awkward, right? So someone makes a new thermometer and they say new thermometer true, and you say, well, what the heck is that, right? You have to go look up the documentation and you have to figure out, oh, they mean a thermometer that measures in Celsius, right? Instead, you can easily make a little enumeration that has only two values in it. Right? So you can make an enumeration called temperature scale, right? And it's got a constant called Celsius and a constant called Fahrenheit, right? And now when someone reads that, they know, oh, you've got a thermometer that measures in Celsius, right? Similarly, your binary digit is 1, and your binary digit here is 0, right? So using enumerations instead of Boolean values makes your code a lot easier to read. If you happen to know the number of constants and you know their values at compile time, then using an enumeration is an appropriate example. So in the notebooks, there's this class called card that represents a playing card. One of the implementations for playing card uses a string to represent the rank and the suit of the card, right? So it takes in the string hearts or diamonds or clubs or spades. Right? Now the problem is when you make a class like that, you have to check the string to make sure it's a valid string, right? And so there's all this validation code that's in that class, which is a real pain in the butt. If you just make an enumeration called suit, right, and it has 4 constants, now your constructor or any other method in the class can just take in a suit object, right? There's only 4 suits, so you don't have to do any validation, right? Similarly, you can make a rank class that represents the ranks of the cards, right? And then again, you don't have to do any validation. So using enumerations in this case really simplifies the implementation. Right? If you're interested in this particular class, just go look in the notebooks for the card class and the enumeration notebook, and you'll find it very quickly. All right, are there any questions about enumerations? They're not super common in the language, but they are useful, they are useful in many niche cases. All right, so I'm just gonna, just give me a second to get the next lecture up and running. So I think the next lecture is, we're moving into part 3 of the course now. So we've basically implemented simple classes. And so now we want to start looking at classes that have somewhat more complicated structure. Enums. Yep. Okay, so we've already seen UML class diagrams, so I'm just going to skip over this part. So we saw this in an earlier lecture, so I'm just going to jump over this quickly. All right, and I want to talk about relationships between classes. So all the classes we've implemented so far, you've got a class, it has some fields. The fields are either primitive types. I think they've all been primitive types so far. Right, so this lecture is relevant when you have a class and it has fields, but the fields are also a reference type. So in an object-oriented program, typically you have multiple interacting classes, right? So there's never, in a normal program, there's never just one class, there's many classes. And so the relationship between your classes becomes important, right? If you have a class that happens to be built using other classes, then the structure of your class depends on other classes, right? You almost certainly have classes that interact with other classes, so the behavior of your class also depends on other classes. We're interested in the structure in this lecture. The behavior of different types, so the way objects interact with one another, that's a topic for probably a third-year course. Maybe a second-year course. Okay, so the relationship between two classes. So dependency is the weakest relationship that you can have between two classes. Right? So dependency models what's called the uses relationship. Right? So one class uses another class. If class X uses a class Y, then we say X depends on Y. Right? Similarly, your two classes, X and Y, it might also be the case that Y depends on X. Right? So dependency can be a two-way relationship. Right? So you'd have two classes that depend on one another. Right? How do you know if two classes depend on one another? Well, one class uses the other class. So X depends on Y. If you have a field Y, that's in X, right? If you have a parameter or in a constructor or method of X that uses Y, right? If one of your methods or constructors internally uses an object of type Y, and I guess this is the same thing. So if one of your methods happens to return an object of type Y, right? Then you say, then it must be the case that X depends on Y. Right? So dependency can be shown in a UML class diagram using a dashed line ending in an open arrow. Right? So the class point2, right, which we've seen so far, we implemented toString for point2. Right? So what does that mean? It has a method that returns a string. Right? So point2 depends on the string class. Right? So dashed open-ended arrow pointing to string. Right? There's another class called vector2, which we didn't talk about in the lectures, but it is in the notebooks. Right? So vector2 also implements toString, and therefore it depends on the string class. It turns out if you look at the full implementation of point2, you'll see that point2 depends on vector2. Right? So there's some method in point2, so you can take 2 points and subtract them, and that gives you a vector. Right? And so there's a little UML class diagram that shows the relationship between these three classes. Right, now you might wonder, where is object in all of this? Right? Because in point2, right, we also implemented equals, right? And equals has object as one of its parameters. Right? So point2 depends on object, but it turns out the relationship between point2 and object is actually a stronger one. And we'll talk about that a little bit later. All right, so there's another type of dependency relationship called association. Right? So association is a stronger form of dependency. Right? And association models the has-a relationship. Right? So dependency is uses, Association is has, right? So in other words, class X has an association relationship with Y if every X object has a Y object, right? So what does that mean? It means if your X class has a field of type Y, there's an association relationship. It can also be the case that Y has an association relationship with X, right? So association can be two-way, just like dependency. Oh, sorry, this is from last year. This is from last term. Is there a better example? All right, so in a UML class diagram, if you want to show the association relationship between two classes, you connect the two classes with a solid line, right? So last year, assignment 3, they had to implement this class called ppm as key reader. So this was a little class that reads in a simple image format, right? That thing there returns or uses that thing there. It has a simple image object inside of it, right? So that reads an image and it stores it in one of these things here. Right? Each reader reads in one object at a time. So each reader object has an association with one simple image object at a time, right? If it could read in multiple objects at a time, that one could be some other number. Right? You would use n if it's an arbitrary number of an arbitrary number. Here's another example. This is out of a, if you read the notes, it tells you where this figure comes from. It's from a classic textbook in object-oriented programming. So this is a UML class diagram where there's a class called show and there's a class called performer, right? So every show has a performer or one or more performers. This line here, right, shows that there's a relationship between show and performer, right? And it also shows that there's an association between these two classes, right? So in other words, every show has a performer, right? It turns out in this case, every performer has one or more shows, or 0 or more shows. So the star indicates 0 or more, right? And you read it from the starting class to the attached class, right? So each show has what's called an so imagine there's a Broadway show, right, or a live play, right? You might have an orchestra. Similarly, you might have a cast, right? So in the orchestra, each show has 0 or more performers, right? A performer might be a performer in 0 or more shows if they're in the orchestra. Similarly, if you're in the cast, so if you're one of the actors, right, each show has 0 or more performers who are actors, right? Each performer might be an actor in 0 or more shows. Right? This one here is showing this the role called backup, right? So if you're an actor, right, and if you're a lead actor, you might have 0 or more understudies, right? So each performer who's a lead actor might have 0 or more understudies. Okay, so association is pretty straightforward, right? So you look at your class, you look at the fields, right? If one or more of your fields is a reference type, right? In other words, if it's an object, right? Then your class has an association relationship with those other classes. All right, so in association, it can have one of two forms, right? So it's either aggregation or composition, right? So aggregation and composition, these are stronger forms of association, right? And so these terms here are used to describe, well, they are used to describe a relationship between two objects, right? Now both terms describe the has-a relationship, so they're just like association, right? So for example, if you were modeling the university as a bunch of classes, right? The university has a collection of departments, right? Every department has a collection of professors. Whoops, sorry. Right? Now the difference between these two terms, right, is that composition implies ownership. Right? So in other words, if the university disappears, right, all of its departments also disappear. right? So you can't have, so there's no such thing as a department of computer science that exists outside of a university. Right? So we would say that a university, you might model this as a composition of departments. Right? Aggregation does not imply sole ownership. Right? So if a department disappears, then it's not necessarily the case that the professors also disappear. Right? Because a professor can be appointed to more than one department, and they can be appointed to more than one university. Right? So for example, if the university gets rid of some department, it's probably the case that the professors are moved or belong to some other department already. Right? So the professors do not normally disappear. In other words, a professor can exist in isolation of a department. Right? So a department, you might model this as an aggregation of professors. Right? In other words, the departments don't own the professors. Right? However, these are both one-way relationships. Right? So in other words, if you have something that's made up of some other type, right, that other type cannot be made up of the first type. Right? So normally we talk about the whole and the part objects. Right? So here the university is the whole object, its departments are the part objects. Right? So the whole is made up of the parts, but the parts are not made up of the whole. Right? And so that's the way to remember it. All right, so you can make this, a simple example here is a person class. Right? And this is a common example that you'll see in most introductory textbooks. It's not a very good example. So you say that a person has a name and a date of birth. They could have lots of other things too. Right? So here we've got a string for the name. We've got a date for the date of birth. If we make a simple implementation of the class, right, we can have a constructor that takes in a name and a birth date, right, and we can write this name equals name, and this birth date equals birth date. Right. For the get name method, we just return the name, and for the get birth date method, we just return the birth date. Right. And so if this is our implementation, then that person class is using aggregation. Right. So the constructor does not make a new copy of the name or the birth date object that's passed to it. Right? So right here, when you write this name equals name and this birth date equals birth date, right, what's happened here is that the person's name object, that one there, right, is the same object as the name that was passed in by the caller. Right? Similarly, the person's birth date object is the same date object that was passed in by the caller. Right? There's no new string here, there's no new date here. So the person object doesn't actually own its name or birth date. Right? It can't own them because it's sharing them with whoever called this method. Right? That is the same object as that. That is the same object as that. Right? Right? So there's no new objects being made, which means the name and birth date objects are shared with whoever called the constructor. Right? And that means both the caller and the person object, they're holding references to the same name and the same birth date object. Right? So for example, if you've got this code here, right, so someone is going to call the person class, the person constructor. Right? So they have a string that represents the name. They have a date object that represents the date. Date's weird. So that's the date, March 26, 1991. And they call the person constructor like that. Right? Then if you were to draw the memory diagram for that picture, you would end up with the following. Right? So the caller of the method, right, they have a string s, that's the name. Right? So there's the name object, there's the string object, sorry. Right? They have a date that represents the birth date, so there's the date object. Right? The caller has a reference to that string object. Right? They have a reference to that date object. Right? When they make the person object, right, there's your person object. Right? The person object also has a reference to that name, that string, sorry, and they have a reference to that date. Right? So notice you've got person object, caller. They're both sharing the same string and date objects. Right? So neither one of them actually owns the string or date. Right? So Right? So the caller has a reference. And the person object has a reference to the same objects. Right? So for the string, it doesn't matter. Right? the string's immutable. Right? So no one can change whatever this string happens to be here. Date, however, is mutable. So you can change the state of a date object and make it represent a different date. Right? So for example, whoever made that person object, right, can take their date and change the year, the month, and the day. So that changes it to November 3rd, 1995. Right? And now if you ask the person object, what is your birth date? Right? Their birth date changes from March 26, 1990 to November 3rd, 1995. Right? Why does it change? Because both the caller and the date, and the person object, they both have a reference to the same date. If one of them changes the date, then the other, either the caller or the person object, also sees the changed date. Right? So because the date instance is shared by the caller and the person object, right, the caller can modify the date, right, and the person sees a new modified birth date. Similarly, the person object can modify the date, and now the caller also sees a changed date. Right? The string, it doesn't matter, right, because neither the client or neither the caller nor the person object can actually modify the string. Right? Strings are immutable. Right? And that makes them easy to use building blocks for other objects. Right? So you never have to worry about sharing a string between more than one object, right? Because the string can't change anyway. Right? So if you can, and if it's not too expensive, right, you should consider using immutable objects when you can. Right? It makes it easy to build your software. It makes it easier to test your software. Right? Because the state of an immutable object never changes. Right? And that means you can share them between multiple different objects and never worry about them changing. All right, so to draw a picture of aggregation, right, it looks the same as association, except you add an open diamond on the whole object. Right? So the person is the whole, right? It's made up of a date and a string. Right? And so when you draw this, right, the diamond goes on person. Right? So person is an aggregation of one date. Right? Person is an aggregation of one string. This is not a great example. We'll do this anyway. So this is the bouncing ball example, right, which I think I showed you in the lecture one day. We didn't look at it in any detail, but that doesn't matter. Right? Okay, so in this bouncing ball program, that ball is a projectile object. Right? The position of that ball is represented by a .2 object. The speed that the ball is moving at is represented by a vector object. Right? In this particular example, the ball has a point that represents its position. The ball has a vector that represents its current speed. Right? And in this particular example, the ball doesn't own either the point or the vector. Right? It shares it freely with whoever makes the ball. Oh, I think it's right here. Okay, so here, here's the class projectile. Right? It's got a .2 object that represents its current position. It's got a vector 2 object that represents its current velocity. Right? The no argument constructor makes a new .2 object and a new vector 2 object. Right? But the method getPosition and getVelocity simply returns a reference to the internal point object and a reference to the internal vector object. Right? So as soon as you call getPosition on a projectile, right, the object that you get back is the same object that the projectile is using to represent its position. Right? If you take the returned point and change its coordinates, then the ball suddenly moves somewhere else. Right? Similarly with getVelocity, if you take the returned vector and change its coordinates, suddenly the ball moves in a different direction. SetPosition is similar. Right? So if you tell the ball to move to a new position P, right, and then internally all it does is set its position object, its point object, to be the same object as P. Right? And setVelocity does the same thing. Right? So if you tell the ball, change your velocity to this vector here, then all it does is change its internal reference to be equal to the new object that was passed in. Right? So it never makes a copy. Oops, sorry. So in get position, right, we never make a copy of the internal position. Right? We just return the point that represents the position. Right? Get velocity never returns a copy of that vector. It just returns that vector. Right? Set position and set velocity, they don't make a copy of the incoming object. Right? It simply sets its internal reference to be the same object as the incoming object. Move is not important in this case. Right? So if you implement projectile using aggregation, it's very easy. You don't do anything different than what we've been doing so far. Right? When you look at these, when you look at the methods, so set position simply changes this position to be equal to p, and that's it. Right? Set velocity simply changes this velocity to be equal to v. Right? So implementing projectile is easy. You just do what we've been doing so far. Right? All of our fields, right? You just treat the objects that are the fields as though they were primitive values. Right? We're not using them in any different way. Right? Our accessor methods, again, you just treat the fields as though they are primitive values. Right? You just return a reference to your internal fields. And similarly with the mutator methods, right? Again, you don't actually do anything special with the objects, right? You just treat them as though they were just plain old variables. So the fields and projectiles, right? Those are just names for some other objects, right? And so the fields are just what are called aliases, right? So they are names for other existing objects. In this little example here, right? Someone's going to create a point and a vector representing the position and velocity of the ball. Right? They're going to make a ball, and they're going to set the position and velocity passing in their objects. Oops, sorry. That should be VEL. Right? So what happens in memory is the following. Right? So the caller has a reference to a point and a vector, right? So they have a reference to that point, right? And they have a reference to that vector, right? And then they make a projectile object. That projectile object has a reference to that point, and it has a reference to that vector, right? So if I ask the ball, what is your position? Right? That returns a 0.2 reference, right? Are they the same object? Right? So is that object the same as that object? Right? If you want to know are two things the same object, you use equals equals, right? And that returns true. Right? Why is it true? Because that value is equal to that value. Right? That's what equals equals does. Right? Okay, so what happens if whoever made that vector there, or sorry, that point there, changes the coordinates of that point, right? So they change the coordinates of their point to minus 99 and minus 22, right? Now, you don't even have to ask the ball for its position, right? You can just use the old reference that was returned by the previous call to get position, right? If you print out that object now, right, that object suddenly is now minus 99 and minus 22. Right? On this line here, it's 10 and 20. Right? Without calling any method on ball position, right, its state suddenly changes to minus 99 and minus 22. Why? Because that object is the same as that object. When the caller changed the state of that object, the state of that object changes as well. Right? So when the caller changes the coordinates to minus 99 and minus 22, right? As far as the ball is concerned, its position is now minus 99 and minus 22. Right? So if a client or if the caller gets a reference to the position or velocity of the projectile, right, then the caller can change the quantities without asking the projectile. Right? So in other words, you can change the position of the ball and never ask the ball to change its position. Right? This is not a flaw. Right? It seems weird, maybe, right? But it's not a flaw of aggregation. right? This is simply a consequence of choosing to use aggregation in this particular example. Right? If you want it to be the case that you must ask the ball to change its position, right? So in other words, if you want that line there to print out 10 and 20, then you have to do something else, right? And so that's what composition is for. And so we'll look at composition in the next lecture. So that's it for today. See you on tomorrow.